Hello and welcome. Today we are looking at magnetic flux and particularly to describe how magnetic flux can change. We have to look at this relationship here where the magnetic flux is equal to the magnetic field that's parallel to an area. Or if it's not parallel, then it's going to be modified by cos theta, where theta is the angle between the area and the magnetic field lines. I have to put in a few caveats here. The vector for an area, very, very strange, is actually um, a, a line that is perpendicular to the face of that area. So in this case, where this pink line here, this pink arrow would be the vector for an area, and these lines would be the magnetic field. In this case, magnetic field is parallel to the area vector. So this is when you have magnetic flux. So cos theta, in this case, theta would be 180 because they're in opposite directions. Cos theta is at a maximum. If you have the case where you have, again, an area, let's put it on its side now, an area like this with the boom, with the vector coming out like that. Now if we extend this magnetic field down here, now our magnetic flux is 0 because these are perpendicular to each other. They're not parallel as we want up here, and cos theta, they are 90 degrees, cos of 90 is 0, making the overall flux 0. So just so you know how the angles work, you want the lines to be going into your area. They're pushing into it, like filling it up. They're going in and coming out the other side like this. Okay, you don't want them skimming the face of it or just going directly behind it without coming through at all. None of that. You want them going inside it. That's how we get this parallel thing. So don't get confused. Parallel works because the area vector is perpendicular to the surface of the area. Okay, now to get on with what the meat of the actual dot point is, which is how magnetic flux can change. And man, there are a lot of ways magnetic flux can change. So many. So first of all, magnetic flux is all those field lines that come out of, say, a bar magnet. So let's just draw a little bar magnet over here. We're going to be using this guy for a few things. So I'm going to try and draw it quite well. I'm going to use red as my magnetic field lines, and they come out somewhat like so. There you go. What a beautiful magnet. And I'm going to draw a little area here. I've drawn it like this to try and get some perspective so you can see the field lines are trying to hit the area like this. The area kind of looks like this to you. The field lines are hitting it like that. So let's say that cos theta is at a maximum. These lines and the pink vector line, they're parallel to each other, right? Okay, I think you can imagine it. So and I'm going to need a few copies of this. So let's copy that. So how magnetic flux can change. Number one, they can change. Let's put a number one there. They can change if we bring the magnet closer to the area. So if we grab the magnet and we bring it closer to it, then more of these lines are going to be going through that area. Or we could bring the area closer to the magnet. So usually when we say an area, it's probably going to be a loop of wire or a sheet of metal or something like that. This is for later on in the topic. So if you move a magnet towards, or if you move a magnet away from it, you're going to change the amount of magnetic flux. And the reason you're changing it is you're changing B. You're changing the amount of magnetic field that is going through the area. Right now we've got one line going through it. If you make this go closer, then 3 of these lines are going to be going through it. If you make it closer again, then it's going to be 5. And similarly, if you move it further back, you're going to make less and less magnetic field lines go through it. So number one, how do you change magnetic flux? You change the strength of magnetic field by moving either the magnet or the metal closer or further away from each other. Okay, the closer things are, the stronger the magnetic field is. Yes. Okay. Number two. Um, Let's do that one. You can change it by stretching out the shape. So let's bring this over here. So if you change, so now we're talking about number two. Now we're talking about changing the area. So this loop here, right now it's a big square sheet of metal. If we put a force on both sides so that we sort of squash it together until it's flattened out into a long, thin sheet like this, right? Not as many field lines are going to go through it. These ones are all going to miss it, and it's not going to have as many going through, okay? This is because we are changing the area. And then conversely, you could have something long and skinny like this, and you could grab the sides of it and stretch it out until it's like a nice big circle. It's probably not going to be that big with this circumference, but there we go. Stretch it out into this big circle. It's got a larger surface area, and more of these lines are going to go through it. So number two, you change the area by squashing your wire, your loop of wire together, squashing it or stretching it out. That's going to change the amount of area that those magnetic field lines can go through. Okay, let's talk rotations. So here we go. If we, yeah, let's put it here. Yep. If we rotate the loop of wire, if we rotate it around like on this axis here, yeah, right now it's up like this, but we're rotating it now like this. Eventually, if it becomes side on, it's going to actually look a lot like what this does up here. We're going to rotate it around um, until it's still just as large. We haven't changed the shape of it, but now it's side on like this, okay? And now when it's side on, those magnetic field lines are going to skim over the top of it or shoot underneath it. Not as many of them are going through, right? We've got this, our sheet of metal here, we've got our magnetic field lines and boom, they're hitting. But when we make it side on, they're going to miss it, go up and down. That is changing, I guess it's sort of changing the angle, right? Now the area vector is perpendicular to the magnetic field. You could also consider it as changing the area, since the area over which the magnetic field is hitting it is much lower. Now that area is just this amount here. It's just hitting that edge rather than hitting the whole thing. Okay, conversely, you don't have to change, um, where are we at? I was writing numbers on some of these things. This was number three. This was also part of number three. You don't have, and this is also kind of part of number three. You don't have to rotate this around. You could also rotate the magnet around. Okay, when you rotate the magnet, these field lines are going to go from away from the wire, and then when it rotates back around to the other side, the magnetic field lines around the south side down here, they're gonna hit it as well. So as you rotate it, it'll get less flux, then more flux again if you keep rotating it the whole way around. Whew, okay, couple more ways if you can believe it or not. Let's look at number four. So here, for this one, I'm going to consider a scenario where our thing is much further away. Um, this is a bit of an interesting one. If you add a piece of ferromagnetic material, so if you add a piece of iron or something like that, you actually will align all the magnetic domains inside that piece of iron, and it will become its own magnet. So by putting this piece of iron here, it becomes a magnet and essentially extends that field out further than where it was just beginning. So instead of just having this field out here, now you've got this field out here. So by extending it further, you can get a magnetic field which is closer to your area rather than not. We have essentially changed B, in this case, increased the amount of magnetic field close to our wire. It's very, very similar to number one, right? We're moving the magnet closer, but instead of moving the magnet closer, we've added in some extra ferromagnetic material. We've sort of added in more magnet in a way. Okay, that is number four. Number 5. For number 5, we're going to have to start thinking about electromagnets. Is this going to fit? Yeah. Okay. So an electromagnet is where instead of having a bar magnet like this, you have a power source attached to a coil of wire, and the coil of wire goes around ferromagnetic material before coming back down, right? The strength of the magnet depends on it depends on the amount of electricity going through. It depends on the current. So increasing the current, so say if this is attached to a power pack, if you increase the voltage on this, that's going to increase the strength of magnetic field. So more field lines are going to be coming out, and that's going to be changing the amount of flux as well. Increasing or decreasing that will do it. And there are all the ways that I can think of that you can change magnetic flux. All of these scenarios are going to be relevant in upcoming lessons when we start looking at how, when the magnetic flux changes, what are the responses to that? And it's a multi-step process. So it's really, really good if you get grounded right now, learn these things. We can call that one number 5. So we have um, moving the magnet or the wire, we have changing the shape of the wire, we have spinning or rotating the wire or the magnet, we have adding in extra ferromagnetic materials, and number 5, if it's an electromagnet, increasing or decreasing the strength of that electromagnet. Good luck learning.